Welcome everybody to this video presentation of the talk entitled Quantum Computing for AI, Hype or Hope. What I wanted to do in this presentation is to talk about the present hype about quantum machine learning and contextualize it a bit, and point out that this is a hype, but still there is hope. And so I thought we also look at an example where quantum computing could potentially contribute to artificial intelligence or machine learning. And in order to do that, I have to ever so briefly go through the essentials of quantum computing theory, and we'll then talk about this example, namely the idea of quantum Bayesian network inference. Let me say this straight away. It might be rough. I will not discuss all the mathematical details. I'll really just give a coarse presentation of what quantum AI or quantum ML could all be about. But first, why do we talk about quantum computing anyway? Well, quantum computing exploits quantum mechanics for information processing. That is, it exploits phenomena such as superposition, entanglement, or quantum tunneling. And using these quantum phenomena, quantum information processing can reach levels of efficiency that are unreachable on digital computers. If all goes well for certain settings, we can realize up to exponential speed up in computing. Theoretically, this is nothing new. It had been worked out in the early 1980s. Theoretical progress was then made in the 1990s when people invented the first quantum algorithms that really work faster than their classical counterparts. And then nothing happened for quite some time, and practical progress in the area of quantum computing basically just happened recently in the 2010s when quantum computers or machines that do quantum computing became practical and became actually commercially available. And at the same time, we all know that in the 2010s and now in the 2020s, we have seen dramatic progress in artificial intelligence, mainly driven by machine learning. And modern machine learning, which is essentially deep learning, is an extremely compute-intensive endeavor. And the quantum computing community therefore jumped on this bandwagon and is actively propagating quantum machine learning as a solution around this computational demands with modern machine learning. So this is going on since the 2010s. We actually already have a couple of textbooks on quantum machine learning and numerous papers. The scientific literature in this area is just exploding. So let us try to look into this current hype around quantum machine learning or QML. At its very heart, quantum mechanics and therefore quantum computing is governed by the Schrödinger equation, which I show on the screen here. There's an interesting quote by Feynman. Where did we get that equation from? Nowhere. It is impossible to derive it from anything you know. It came out of the mind of Schrödinger. That's quite telling for what we're going to discuss in a minute. If we look at this Schrödinger equation, it looks a bit funny, so probably have to look at the ingredients of this equation. First of all, I is the imaginary unit, h bar is the reduced Planck constant. There was this differential operator ddt. It is a linear operator. And then this psi of t in the pointy brackets is what physicists call a ket vector. This is really just another way of writing down vectors as we all know them. But what is crucial here is that these vectors, these ket vectors, represent the state of a quantum system at some time t. And then finally, we had this ingredient h of t. This is a Hermitian energy operator, which is just another linear operator. Now, since the imaginary unit I features prominently in the Schrödinger equation, and since we have all these operators, linear operators, we realize that quantum computing is basically just complex valued linear algebra. In a sense, that makes it easy. In another sense, that makes it complicated. Because if we live in this world governed by the Schrödinger equation and live in this world where we have quantum systems whose states we could manipulate through operators, we have to realize that present-day quantum computing is very much bit-level programming. That means that we do not have, at least not natively, abstract data structures such as lists, trees, heaps. We do not have common control flows such as for while loops or if then else statements. We don't even have access to variable assignments such as x equals x plus 1. There's a fundamental quantum mechanical theorem that's called the no cloning theorem that forbids that. And if we look at this, then this already means that quantum computing algorithms differ quite substantially from the kind of algorithms we're all familiar with. There's further limitations with respect to quantum computing. They are rather practical because up until today, there is no such thing as a universal quantum computer. That is, right now, we do not have any device, technical device, that could reliably manipulate arbitrary many quantum bits or qubits. There is, up until today, no device that would allow for arbitrarily complex operations on these quantum states. And even more critically, there is no such thing as a quantum random access memory. All of this is to say that present-day quantum computers are so-called noisy intermediate scale quantum devices or NISQ devices. That is, they can only manipulate a few qubits, intermediate scale. They suffer from early decoherence. Maintaining these quantum states is quite difficult. And if you can do this only for a short period of time, then you may not be able to finish the kind of computation you actually wanted to do. There's only a limited set of operators. There is measurement noise. And again, there is no QRAM. Even if there was a universal quantum computer, we have to keep in mind that it could be extremely expensive to encode digital data into quantum states. If we want to work with the kind of data that surrounds us in our daily lives, we would have to encode them such that a quantum computer can work with that. That might be very expensive. It may also be very expensive to read out quantum data or quantum states back into digital computers. This is called the I/O problem, and it means that it can nullify any quantum advantage. That is, even if we had an exponentially faster quantum algorithm, its effects might be completely nullified by the fact that it may be very expensive to put data on a quantum computer and to get it out of a quantum computer. And this is the problem with the current quantum machine learning hype, because the QML community blissfully ignores all these issues, theoretical and practical. And this is a personal opinion of mine. I'd say that more than 90% of this really rapidly growing quantum machine learning literature reports fanciful fantasies of no practical value whatsoever. This is well known. I'm not the first to say that. This is well known, has been eminently critiqued before, for instance, by Childs or Scott Aronson, who really point out that much of what is being published these days makes assumptions or is built upon assumptions which just do not hold yet or are very limiting with respect to what you can actually do in practice. Again, the quantum machine learning community knows that and has devised their own workarounds around these kind of problems. And a very popular current technique are the so-called variational quantum algorithms, where we have feedback loops between quantum algorithms and classical algorithms. They basically work like that a classical optimizer is used to adjust parameterized quantum circuits towards a given problem. The quantum circuit does a computation. We measure its results. We use these results to optimize the circuit classically and continue until we've hit a stable point. This makes a lot of sense in areas such as quantum chemistry, where people are interested in coming up with quantum circuits that model complicated quantum systems, such as large molecules or so. But this is not quantum machine learning. Variational quantum algorithms learn on digital computers and therefore do not learn faster than classically possible. So really, we are dealing with a hype, but there's hope. And the fundamental observation could be that we might want to try not to force classical algorithms into the quantum realm, but to look at problems or for problems which naturally would allow for quantum computing implementations. So the idea would be to look out for AI and ML problems which can easily be implemented within this framework of quantum computing. This is indeed how all the presently known quantum advantages algorithms have been devised or developed or invented, like Shor's factorization or Grover's search, didn't force a classical problem into the quantum realm, but started with the observation, hey, that this kind of problem seems to work well in the quantum domain. So now we're prepared to have a look at how this could look in practice. But first of all, ever so briefly, we need to talk about essential quantum computing theory. That's basically the four postulates at the heart of quantum computing. First of all, first postulate is that at any point in time, a pure quantum system is characterized by a state vector of unit length in a complex valued Hilbert space. The canonical example for such a quantum system would be a quantum bit or qubit, which is a two-state quantum system. That is, it is a quantum system that can exist in a superposition of two basis states. These basis states are orthogonal and usually written as ket0 and ket1. For those who are not really familiar with this kind of notation, just think of ket0 as the vector 1, 0 and ket1 as the vector 0, 1, so they are orthogonal. Note that these two basis vectors come with coefficients in front of them, alpha naught and alpha 1. They're called the amplitudes of this state. And very crucially, if it is a quantum state, it has to be a unit vector. So these amplitudes are complex valued numbers who have to obey the normalization condition such that their norm squared adds to 1. The second postulate in quantum computing is again that the evolution of a closed quantum system is governed by the Schrödinger equation. I will not read it out. I'll give you a somewhat simplified version of this postulate. It can also be shown that from the Schrödinger equation, it follows that the change in state of a closed quantum system over a very short period of time corresponds to a unitary operation on the state vector. So we'll get a psi dash is the result of applying a unitary operator u on the state psi. And when it comes to quantum computing, we have a pictorial representation of this idea. In quantum computing, we typically visualize qubits, systems of qubits, and the operators acting on them in terms of quantum circuits. And I've shown one on the very left where we have some generic operators u, which may act on a single qubit or on 2 or even 3 of them in this example. And of course, these boxes u, we would have to specify what is in them. What we see on the left may stand for what we see in the middle without explanations. There's interactions between qubits here. And I've plotted a couple of operations here, which in the literature are typically abbreviated like that. So this is really just to say that we have a system of qubits and there's operations acting on them, and we read the information flow from the left to the right. Third postulate is that we can measure the state of a quantum system, but if we do this, then it will collapse to one of its basis states. It will collapse to one of the eigenstates of the measurement operator we apply, and the probability for collapsing to one of these states is actually encoded in these squared norms of the amplitudes of these states. Very, very crucially, quantum measurements are probabilistic. And that means that we can ever only extract a single bit of classical information from a qubit. Measuring the state of a quantum bit or of a system of quantum bits means to transform quantum information into classical information, or even critically, or more critically, even though a quantum bit or a system of them can exist in a superposition state, so basically in super many states, if we measure the quantum system, all we can get is one of these basis states the qubit might be in. And finally, if already talked about systems of qubits, fourth postulate, state spaces of composite quantum systems are tensor product states. If we have a system composed of two subsystems, say psi and phi, then the state of the combined system can be modeled as the tensor product of the state psi and the state phi. And just for the fun of it, I will not read this slide. Here is an example where I'm looking at a system of 3 quantum bits, a register of 3 quantum bits. Each of these quantum bits can be in a superposition of the basis states 0 and 1. And if we then compute the tensor product of these 3 states, we get a very lengthy expression from which we can read the fact that these 3 quantum bits together live in an 8-dimensional space, because this tensor product expresses a superposition over 8 basis states. And here I have written that in coordinates. Again, I will not read it out. The take-home message is, though, that the joint state of a system of n qubits corresponds to a 2 to the n-dimensional vector. Quantum state spaces are exponentially large. That is one of the fundamental advantages we have in quantum computing, but nobody knows how nature does that. Nobody knows where nature stores all this information. Why does this crazy linear algebraic framework work? Why does this describe quantum mechanics? It may be futile to ask this. It might be futile to ask why quantum states are complex tensor product unit vectors. They just are. Might be futile to ask why observable properties of a quantum system correspond to certain linear operators and why measurement results in an eigenvalue of said operator. It just does. We have to attribute this to the unreasonable effectiveness of mathematics in the natural sciences. Humanity doesn't know why nature follows certain laws. She simply does, and here all we can hope for is to be able to recover these laws and to work with them. Okay, now we're prepared to have a look at an example where quantum computing could be beneficial for artificial intelligence, and this example has to do with Bayesian network inference. So let me therefore first have a look at the classical scenario. What we see on this slide is a very small Bayesian network consisting of three random variables with dependencies among them. And if we look at this visual representation of a Bayesian network, we recall that we have to read this as the joint probability over these three random variables can be factored as dictated by this diagram. For instance, in this case, we would have that the joint probability P of x and y and z can be expressed as the probability of z conditioned on x and y times the probability of y conditioned on x times the probability of x. Why are people interested in graphical models such as this? They allow us to do causal inference. And I wanted to go through an example. And for the sake of simplicity, the example we will be looking at will be a base net over Bernoulli random variables. So let's assume that this graphical model, this Bayesian network, represents the situation where we can ask what causes success in school. Say the random variable z reflects the fact whether or not you passed the last exam. That may depend on the fact whether or not you learned for the exam, y. And learning for an exam and passing the exam may both be conditioned on being smart, and I'll refer to being smart as x. And what we see at the bottom of the slide are three probability tables, which I basically have made up, but we can also ascribe them to experience with students. For instance, could say that 75% of people are not really super outstandingly smart, but only 25% of them are. We might have probabilities for how likely is it to learn for an exam, given that you are not really smart or given that you are smart. And we may have probabilities for passing an exam, given that you learned or not and that you're smart or not. So I made these numbers up just for an example. With a model like this and all the information contained in these probability tables, we can then perform inference and ask questions such as, how likely did you learn, y equals 1, given that you are smart, x equals 1, and passed, z equals 1. So what we are asking for is the conditional probability for y being 1, given that x and z are 1. We can rewrite this expression like so, plug in all the numbers from our probability tables and find that there is about 80% chance that you learned, given that you are smart and passed the exam. You can also ask, how likely did you learn? Y equals 1, given that you are smart, x equals 1, but failed, z equals 0. Walk through the motions again and find that this would amount to about 35% chance. In this super simple example, it is easy for us to answer these two kinds of questions because the setting here is very, very simple. We only deal with a few random variables, 3 of them, and are given evidence, so background information for many of them. So here we have 3 random variables, and for 2 of them, we know their values. And therefore, we only have to marginalize over one of the 3 variables. By marginalization, I mean we have to compute these kind of summations here to marginalize out the value of y. In this example, we only have to do this for the random variable y. However, in general, we may have a lot of random variables and typically evidence for only few of them. And in situations like these, we would have to marginalize over a lot of random variables. And for our Bernoulli variables, that would mean we would have to perform computations of the order of 2 to the n minus k, so exponentially many computations. Long story short, this example suggests, and it does indeed hold in general, that in general, inference over Bayesian networks is exponentially expensive. And a classical workaround this exponential costs is sampling methods. There are many of them. A very simple one is called rejection sampling. Again, I will not go through all the details of this algorithm, but what we basically do here is we randomly sample values for our random variables, in our case x, y, z, and then compute the joint probabilities. And whenever the values we sample agree with the evidence we have, we keep it in our results. And at the end, we can look at how many of the samples we did actually produced a situation that would comply with the evidence, and we can use these samples to estimate the probabilities we are after. And I have done this for this super simple setting. I have performed rejection sampling with 10,000 iterations. And for the two questions I've asked earlier, I found empirically generated probabilities, not pen and paper, but really via sampling and practical computation on a computer. I basically recovered the probabilities we've found using the pen and paper method. But what is shocking, if we look at how I obtained these numerical estimates for the questions we were after, is that 80% of the samples I generated when I tried to answer question 1 had to be rejected because they didn't agree with the evidence. And for question 2, it was actually 95% of the answers that I had to reject because they didn't agree with the evidence. So long story short, rejection sampling works well, but is extremely wasteful when it comes to compute time. And this then leads us to quantum computing for artificial intelligence, for causal inference, for Bayesian network inference. Now, brace yourself, because once again, what we have to basically be able to compute if we do this is probabilities, all the joint probabilities we can have in settings such as this. And again, there's exponentially many of them. Again, we're talking about networks over Bernoulli random variables, which can only be 0 or 1. But if we have n of them, then there is 2 to the n possible states the network can be in. And we would have to infer the probabilities for all these states. That is exponentially expensive. However, and this is a bold claim, I claim that the quantum circuit we see here implements our Bayesian network and computes all the joint probabilities simultaneously. I will not go into the details as to what we see here. I just point out that we have 3 qubits representing our 3 random variables, x, y, and z. And then there is a sequence of computations I do on the first and second, second, and third qubit, which produce a quantum state for which I claim, again without proof, that if we start this quantum circuit with an initialization where all our qubits are in the 0 state, it will produce a superposition state over 8 basis vectors, because we implicitly compute in an 8-dimensional space when we have 3 qubits. And here are the 8 basis vectors for which this circuit will create a superposition. And what's really interesting, and again without proof, one can show that the amplitudes associated with these basis states reflect the corresponding joint probabilities. In a nutshell, this means that the quantum circuit we just saw in one run computes the exponentially many joint probabilities these 3 variables can be in just a single run. However, we have to keep in mind that even though this information is now encoded in the quantum state at the end of the circuit, we can't really get it. Because if we measure that state, it will collapse to one of the 8 basis states and therefore only reveal one of the 8 possible joint probabilities. And that means in order to really estimate them using our quantum circuit, we have to run this circuit several times, perform measurements, and then basically are in the same realm as we are when we do classical rejection sampling. So I have done that using Qiskit. And these are the probabilities I could estimate this way. And if we compare them to the ground truth, which we can easily get in this example with just 3 random variables, we see that, yes, by and large, it seems to work. The quantum circuit is able to produce these joint probabilities. They are a bit off. That has to do with the fact that quantum measurements are probabilistic, but if we do it often enough, I've done it for 10,000 times, we'll get these estimates which are really close to the ones we would expect in our setting. And this allows us to actually perform this kind of Bayesian inference we've seen in the example before, because we can count how often did we see this state and this state, which reflect sort of like the situations in the 2 questions I asked. And we can use that, normalize it by the number of experiments we did to actually get estimates for the inference questions we had. So this is really just quantum rejection sampling, where I do exactly the same thing with a quantum circuit as I've done with the classical algorithm. Now, if we do this, we might ask how good are the estimates we get? And to assess that, I have performed 100 computations with this circuit and 10,000. And for the first inference question, like how likely did you learn given that you're smart and passed the exam, we'll get with 100 runs of this quantum circuit about 0.71. With 10,000, I get 0.79, and the ground truth, if you remember, was about 0.79. So if we look at this table here, then that suggests that so far we haven't had any quantum advantage, because we still need to perform a lot of run-throughs in order to get good estimates. However, now comes the quantum advantage. In what follows, I will abbreviate this whole circuit in terms of just one operator, and I will refer to it as A. And then I will use this operator A, this is basically the computation we have performed so far, and add a couple of further operators to this quantum circuit. And my claim is that if we run this quantum circuit, again without details, we only need to do a few shots in order to get a good estimate for the conditional probability we want to determine. Without details, the interior of these operators SE and S naught looks like this. And I have run this extended quantum circuit again for 100 iterations and for 10,000 iterations. And the super crucial observation is that with this extended circuit, 100 run-throughs give us an estimate that is in the same ballpark as the ground truth. Again, for 10,000, we get something similar as we've already seen, but this time around, only 100 run-throughs are sufficient to get a very good estimate, a very good answer to the problem we wanted to solve. Note that 100 is the square root of 10,000. Now, what sorcery is this? How can a quantum circuit do that? What we have seen in action here is the benefits of a quantum computing technique called amplitude amplification. This amplitude amplification is at the heart of the famous Grover algorithm, but as we've just seen, we can also use that in other contexts. There is no classical counterpart for this kind of computation. We can really only do that on a quantum computer. And in situations where it applies, we have a guarantee that it can reduce computational efforts from O of n to O of square root of n. So from 10,000 runs, we could reduce it to 100. Long story short, amplitude amplification is known where it applies to yield quadratic quantum speed up. And that can be already quite substantial if I only have to perform 100 iterations of the algorithm instead of 10,000, say. I am super well aware of the fact that all of this is extremely rough and very hard to follow if you have no solid background in quantum computing. For the sake of time and sanity, I therefore refer to a couple of lecture notes I've written about this particular idea. They are openly accessible on ResearchGate, and I will add more of them in the near future. So, in summary, the good news is quantum computing harnesses quantum phenomena for information processing, and for certain tasks, this can result in quadratic or even exponential speed up over digital computing. And again, the good news is that this is now becoming practical. We now have first prototypes of quantum computers who show that this really works in practice. The bad news is this really only applies to certain rather specific problem settings, at least naturally. And in the quantum machine learning literature, people try to force classical settings into this framework, and that comes at a cost, typically based on the assumption that we had an all-powerful quantum computer, which we have not. So really, a lot of what we read in the quantum machine learning literature at this point in time is severely exaggerated. However, we've just seen that there are problems in artificial intelligence or machine learning which lend themselves quite naturally to implementations on quantum computers, for which we can therefore quite naturally harvest quantum advantages. So the good news is there seem to be problems known in AI and ML that really allow for faster solutions on a quantum computer. The bad news is that up until right now, we can't really use that to work on problems at a scale that would be interesting in this day and age, because present-day quantum computers show that it is possible, but they are not robust or technically mature enough to actually solve large-scale problems on a quantum computer. So we have to hope that they continue to develop, and if they do, then eventually we can do these difficult, exponentially difficult problems on quantum computers and do them faster there than classically. And that is all I wanted to talk about. Thanks for your attention.